Hello everyone. Today we will start our formal discussion on the MOSFET electrostatics, and I have written down the name of the topic to be MOS Electrostatics, which means metal oxide semiconductor electrostatics, because we are only concerned about the metal oxide semiconductor part of the MOSFET for the moment. And you might recall that in the previous class we finished our discussion on the Landauer transport theory for the MOSFET, so which accounts for the velocity saturation in the ballistic MOSFET as well. So apart from studying the current and the channel charge as a function of various Fermi-Dirac integrals and as a function of VGS and VDS, we studied one of the important things that we studied was velocity saturation in a ballistic MOSFET as well. So I hope this idea is clear by now, and we started our discussion of the MOSFET electrostatics, which mainly accounts for the charge in the MOSFET, and this charge in the MOSFET is directly correlated to the potential in the semiconductor, because the charge in the MOSFET is the charge in the semiconductor channel, and that depends on the potential, the electrostatics potential in the semiconductor. So in the electrostatics we are quite concerned about the charge, its relationship with the electrostatics potential, and that relationship is established by the Poisson's equation for the MOSFETs. And in the last class you might have seen that our main emphasis was about discussing the electrostatics in the y direction, and this point I have pointed out earlier as well, that generally in long MOSFETs, in conventional MOSFETs, what happens is that the electric field in this direction, which means the electric field in x direction, is extremely small as compared to the electric field in y direction, especially in the channel. That was the case for the conventional MOSFETs, but in modern MOSFETs, since this device length is shrinking, so the electric field in this direction, the x electric field, is also becoming comparable, is also becoming dominant. Okay. So in the long channel MOSFETs, that is why we were mostly concerned about the electrostatics in the y direction only, but in modern day devices we should consider this x direction electric field as well, and that is why we should discuss the 2D electrostatics, and that is what we will also study in after this discussion of the basics of the electrostatics. Okay. So in the last class we started with the discussion of the electrostatics for conventional MOSFETs, and as you can see that we used the band diagram as a tool to understand the charge and the potential function, electrostatic potential in the semiconductor. This is the band diagram of the semiconductor when there is no gate voltage, but as soon as we apply a gate voltage, this is how the band diagram looks like. So if there is a positive gate voltage, it will actually deplete holes from the semiconductor. We are assuming a p-type substrate, so there would be a lot of holes in this substrate. So a positive potential on the gate terminal will deplete holes in the semiconductor, which will essentially result in a depletion regime, and the bands, the p-type bands look like this. The Fermi level is quite close to the valence band in the semiconductor, and but close to the interface between the semiconductor and the oxide, because of the depletion of the holes, this Fermi level is now removed from the conduction and valence bands, and this is how it looks like. So generally these bands are drawn in this direction, and these are drawn for this MOS device. M means metal, which is the gate, O means oxide, and S is the semiconductor. So generally these bands are representative of the MOS electrostatics, these bands. Okay. Metal oxide semiconductor electrostatics. And this is the Poisson equation that gives a relationship between the electrostatic potential and the charge distribution in the space. So this is a qualitative way to understand, this is an intuitive way to understand the MOSFET electrostatics. A more mathematical way is by solving the Poisson equation, and that is what we will do right away. So, the total charge in the semiconductor, in any general semiconductor, is actually the charge because of the mobile charge carriers, which means the holes and electrons. So, the total charge will be the charge of the holes minus the charge of the electrons, and the charge will also be because of the dopant atoms. This will be the static charge. So, the donor atoms will contribute as a positive charge, and acceptor atoms will contribute as negative charge. So, this is the charge density in any general semiconductor material. So, if we have an arbitrary doping in a semiconductor, then at any point in the semiconductor the charge is given by the charge of the holes minus the charge of electrons plus the charge of ionized dopants, donors, minus the charge of the ionized acceptors, because ionized donors are positively charged and ionized acceptors are negatively charged. So, that is what we also take in this expression. And as you know that we are mostly concerned about the MOS electrostatics, which is the electrostatics in the y direction. So, the charge density, so to say, so this is the device in the y direction. We have a gate, we have an oxide, and we have a semiconductor. Okay. Generally, this point is considered to be the y equal to 0 point, this interface, and we try to study the electrostatics, or we try to study the charge and potential in the semiconductor. Okay. So, this is metal, this is oxide, this is semiconductor. This is p type. And when a positive voltage is applied on the gate terminal, in that case what happens is that a negative charge is accumulated, and for very high gate voltage an inversion layer of the electrons is created at the interface. And so, this inversion layer is extremely thin actually, this is like a quasi 2D layer, and so that is why the charge or the sheet charge density of this inversion layer is calculated in coulombs per meter square or coulombs per centimeter square. Okay. And this is, so in order to see the charge in y direction or in the charge in the this semiconductor as a function of or the sheet charge density in the semiconductor, we need to integrate this total charge in y direction. So, that will give us the total charge per unit area in xz direction, which will further help us understand the sheet charge density of the inversion layer. But at the moment we are trying to understand the total charge that is accumulated in the material because of the gate voltage, which creates electric field in y direction, and so that is why we take integration in y direction. So, the total charge is given as the charge density integrated in y direction. So, that will have the unit of coulomb per meter square. And this charge density in a semiconductor is P minus N plus Nd plus minus Na minus. Q accounts for the, so this is the number, Q makes it the coulomb, the charge, and integrated from 0 to infinity, which means from interface to deep inside the semiconductor. So, and this is the total charge, and the mobile charge in the semiconductor will be, so these the dopant atoms are the static charge. So, the mobile charge will be just because of these two components, because of the holes and because of the electrons. And in inversion layer in inversion of the, during the operation of the MOSFET, in inversion, the number of holes at the interface are extremely small in number. So the only charge that is left is the charge because of the electrons. So that is actually the mobile charge for electrons in the, or mobile charge in a MOSFET or in a MOS device in inversion layer. Similarly, the mobile charge in accumulation would be, accumulation means when a negative voltage is applied on the gate terminal and lot of holes are attracted to the interface and it will have accumulation of holes. So that will be given by P naught y dy. Okay. So this is how we calculate. So this is the charge of our interest, because these two charges, this is in the accumulation, this is in the inversion, and generally this inversion regime is the most important regime for a MOSFET device. Okay. So, so we apply the Poisson equation. The Poisson equation says that d to psi by dy square is equal to minus q by epsilon s times the, or minus charge density divided by epsilon s, and the charge density is actually this. This is, this charge density q times P naught is in coulomb per meter cube. So this quantity in this circle is in coulomb per meter cube. So this is what we take in the Poisson equation, and in a p-type semiconductor, which is generally the semiconductor in an NMOS, which is actually the semiconductor in NMOS, the dopant atoms are not there. We can assume that there is no dopant atom. So this Nd becomes 0, and we can also fairly assume that Na minus, which is the ionized acceptor atoms, these are equal to the total acceptor atom, which means that all the acceptor atoms are now ionized. So this Na minus is equal to Na. And in the bulk, which means that deep inside the semiconductor, far away from the interface, we can assume the space charge neutrality. Space charge neutrality means that the net charge because of the mobile charge and the static charge is 0. So the charge of holes is Pb, minus Nb is the electronic charge, minus Na is the charge due to acceptor atoms. So this should be 0. This should be 0. So which means that Na, the acceptor atoms are Pb minus Nb, where Pb is the bulk hole concentration, which means the number of holes per unit volume in the bulk deep inside the semiconductor. Nb is the bulk electron concentration, bulk electron density in a way, number of electrons per unit volume deep inside the semiconductor. So, but generally in an n-type material what happens is, so this Na turns out to be Pb minus Nb, but Nb is extremely small as compared to the Pb value. So it can be assumed with reasonable accuracy that Pb is almost equal to Na. So the number of holes in the bulk of the semiconductor is equal to the number of acceptor atoms in the semiconductor, and this Nb, which is number of electrons, will be given by this relationship from carrier statistics. So this will be Ni square divided by Na. Okay. So Nb is the number of electrons in the bulk, or the electron density in the bulk. Pb is the electron density in the bulk. It is equal to the number of acceptor atoms, and Nb is Ni square by Na. So now using these values in this Poisson equation, this original Poisson equation, we will now see that this equation, this Nd becomes 0, Na can be written as Na minus can be written as Na, and Na can be written as Pb minus Nb. So it becomes Nb minus Pb. So now this Nb and Pb values can be obtained from here. So this Nb is written as Ni square divided by Na, and Pb is written as minus Na. This is the Poisson equation for a semiconductor, for a general semiconductor. So, at any point y, so in the y direction, this is the direction in which we are trying to understand the electrostatics. The double derivative, the second derivative of the electrostatic potential is minus q by epsilon s, where epsilon s is the dielectric constant of the semiconductor, is P, is number of holes at that point minus Na minus number of electrons at that point plus Ni square by Na. Okay. So, now if you see this equation, in this equation we have three unknowns essentially. We have this psi y is unknown, which means if we apply a certain gate voltage, we need to find out what is the psi y. Also this P naught y and N naught y are also unknowns, because we also do not know what are these values. Because on application of the gate voltage, there might be accumulation of holes, there might be depletion of holes, there might be inversion layer. So these quantities are also unknown. So there are three unknowns in this equation. So one equation, three unknowns cannot be solved. So we need two more equations, and that's what we dig out. So the two more equations are, they come from the band diagram essentially. So if this is the potential profile, electrostatic potential versus y in the semiconductor, this will be the band profile in the y direction. Okay. And at any arbitrary point y here, let us say we are considering this point here, at any arbitrary point, the number of electrons here, which means, or number of holes, anything, number of electrons here will be number of electrons in the bulk times exponential q psi divided by kt, q psi y by kt. Because if psi y is positive, the bands will be bent down, and in that case number of electrons will increase, and this increase is directly exponentially related to the, so the number or the carrier density is exponentially related to the bending, to the potential. That, and this comes from the basics of the carrier statistics in the semiconductors. This is basic 101 type equation actually. So at any point y, the number of electrons when there is a non-zero potential at that point is Nb, which is the number of potential in the bulk, which means number of electrons in the bulk. Nb is the number of electrons or electron density in the bulk, and by bulk we mean that the potential is 0 in the bulk. So bulk is a point where the potential is 0. So N naught y is Nb times exponential q psi y by kt. So similarly, the number of holes at any point is related to the number of holes in the bulk, and bulk is the region where the electrostatic potential is 0, exponential minus q psi y by kt. So apart from this Poisson equation, we have now these two more equations, and these two equations come from the basics of the semiconductor carrier statistics. And now using these three equations, we can solve, in principle we can solve for the three variables, three unknowns, and the three unknowns are psi y, n naught y and p naught y. So that's what we do, and Pb is Na essentially, Nb is Ni square by Na, and if we do, if we put all these things in Poisson equation, this is what we obtain essentially. d2 psi by dy square is minus q by epsilon s, Na times exponential q psi y by kt minus 1 minus Ni square by Na exponential q psi y by kt minus 1. So this equation is now the equation in a single variable, that is the electrostatic potential in the semiconductor at any arbitrary point y, psi y essentially. And on the left hand side of this equation we have the second derivative of the potential. On the right hand side we have a complex function, I would say complex function of psi y. But in principle, by solving this equation, which is also known as the Poisson-Boltzmann equation, because this is a combination of the this comes from the Poisson and the carrier statistics, that is why the name Poisson-Boltzmann equation. This equation tells us about, or this equation can precisely give us the electrostatic potential at any point y in the semiconductor when an arbitrary gate voltage is applied to the device. Okay. And in order to do this, we would also need the boundary conditions, and the boundary conditions would be that the electrostatic potential at right at the interface at y equal to 0 is psi s, and the electrostatic potential deep inside the semiconductor is 0. So with these two boundary conditions and this Poisson-Boltzmann equation, we can solve for the potential in the semiconductor. And this is one of the main, I would say this is one of the main things that we study in the MOSFET electrostatics, that is the electrostatic potential inside the semiconductor. So this equation is not so easy to solve actually, by the way, because you can see that we have the second derivative of potential on the left hand side, and on the right hand side we have the exponential function. So it is quite an involved calculation, and generally the solution is done numerically. So generally we use numerical techniques, the softwares, to solve for the electrostatic potential. But as you can see from this discussion that in order to obtain the electrostatic potential profile in the semiconductor, we need to at least know this psi s parameter, which is the voltage, or which is the potential at the interface of the oxide and the semiconductor, which is the value of psi at this point. And this is one of the key things that we that is there actually in this in the electrostatics that we need to figure out, because once this is there, then by using the Poisson-Boltzmann equation we can numerically find out the entire distribution of the potential inside the semiconductor. So this becomes one of our key things to figure out in our discussion of electrostatics, psi s, and this psi s is actually set by the gate voltage. It is determined by the gate voltage. Okay. So that is how this effect of the gate voltage comes on the electrostatic potential in the semiconductor. Okay. So this equation, Poisson-Boltzmann equation, is solved in strong accumulation, depletion and inversion region with certain approximations. So that is what we will see, and the easiest one is the depletion region. So the depletion region is the region in an NMOS. So please remember that in an NMOS, the semiconductor, the bulk semiconductor is p type, and this is how the NMOS looks like. So the source, the drain, this is a p type semiconductor that is there, oxide and gate. Okay. So this is oxide. So when a positive voltage is applied on the gate terminal, that repels the holes and a depletion of holes happen, and for a more stronger positive voltage, for a larger positive voltage, the minority carrier electrons accumulate at the interface, and that is known as the inversion region. So before the inversion, the region of operation, this region is known as the depletion region. So before the electrons are accumulated at the interface of the oxide and the semiconductor, before that this is known as the depletion region of the MOSFET, and the depletion region is actually easiest to deal with. So that is why we took it first, because we can precisely calculate, precisely solve the Poisson equation in this region. this is how it looks like. We have applied, so this is the band diagram, this is the gate side, this is the oxide, and this is the semiconductor. So this is metal, this is oxide, this is semiconductor, and as you can see that we have applied a positive voltage on the gate terminal, which has brought down the Fermi level of the gate. Initially the Fermi level of the gate and the semiconductor were assumed to be aligned to each other. So this was also flat, this oxide conduction band edge was also flat, but because of the positive gate voltage now, the Fermi level of the gate comes down, and that results in depletion of the semiconductor. The holes are depleted from here, which results in band bending. But please be careful here, because although the conduction band and the valence bands are bending, but the Fermi level is still uniform across the semiconductor, entire semiconductor. Please take a moment and think about it, why the Fermi level is still constant. Even if we have applied a gate voltage, even in that case the Fermi level is still a uniform energy level across the semiconductor. Okay. So the answer to this is that even if we apply a gate voltage, because of the oxide in between, there cannot be any flow of electrons, although on application of gate voltage the charge would like to flow, but this oxide will block any kind of charge flow. So that's why there is no net current in the device. So net current is 0, which means that the Fermi level must be uniform across the entire semiconductor. So in this in the depletion region, this is we start with the charge density distribution. This is how we write it down, and in the depletion region what happens is that the depletion of holes is there up to a certain width, which is known as the depletion width, and this is represented as WD. So before WD, from y equal to 0 to y equal to WD, holes are depleted, and for y greater than WD there is no depletion region, it is just a normal semiconductor. So the charge distribution looks like this. Rho y is given as minus q times Na for y less than WD. We are assuming that all the holes are taken away, although in practice or in reality that is not the case. There is a distribution of holes, but an ideal approximation is, which is also known as the depletion approximation, that in the depletion region the mobile charge carriers are not there. So which means that the charge density rho y is minus q times Na for y less than WD. In the depletion width the charge density is this, and after the depletion width the net charge will be 0, because after the depletion width the mobile charge, this holes, will neutralize the acceptor atoms. Anyway, the electrons are very less in number and donor atoms are not there. Okay, so finally this is the key point here, that in the depletion region we can approximate the charge distribution by this equation, and the approximation here is that we assume that in the depletion width all the holes have been depleted out of the semiconductor. So that's why we can write rho y to be minus q times Na. Now using this Poisson equation becomes quite simple now. So the Poisson equation will be now, ideally it should be y here. So del dot D, so we should start with this equation, which is equal to charge. So which means that in y direction dd by dy is equal to minus q Na, and D can be written as E times electric field times epsilon s minus q Na by epsilon s, which means that E as a function of y, or if we integrate on both sides, dE is minus q Na by epsilon s dy. Okay. Also, because the net charge is 0 in the deep inside the semiconductor beyond the depletion region, the electric field will also be 0. So, the electric field just after WD is 0, and we need to see what is the electric field inside the depletion region. So, the electric field, if we integrate it from an arbitrary point y to WD, so at any arbitrary point y, the electric field will be Ey, and at WD the electric field will be 0. So, the integration limits are from Ey to 0, and here the integration limits are y to WD. So, if we integrate it like this, on the left hand side we obtain minus Ey, on the right hand side we have minus Qna times Qna divided by epsilon s times WD minus y. Negative sign goes away. So, this electric field as a function of y is given by this expression, which is Qna by epsilon s WD minus y. This is the case in depletion approximation, and we are assuming that the doping density is uniform. Okay. Now, with this we can easily calculate the potential distribution as well. The potential function, if you recall the relationship between the potential and, so the electric field is essentially minus del y, so which means that potential can be written as minus, okay. Potential deep inside the semiconductor is 0, so at y equal to infinity, y equal to infinity is generally the point which is deep inside the semiconductor, and there the potential is also 0. So, generally this is how it looks like, and the limits are from at any arbitrary point y where the potential is psi y to infinity where potential is 0. So, psi y will be equal to minus infinity to y e y prime dy prime. So, these are the basic equations of electrostatics. I am just reviewing it for the sake of completion of this discussion. Now, you see that in depletion region this electric field is just a function of y, a linear function of y, and if we integrate with this value of the electric field, in this equation if we put minus infinity to y e dy, so if we put y to be 0, so this psi 0 becomes psi s, and if we assume a linear electric field, then we obtain this EWD by 2. If we assume that the electric field, or this is the E as a function of y is linear, in that case if Es is the electric field at the interface at y equal to 0, then this right hand side integral will just be the area under this curve, which will be Es times WD by 2. So, this is what we obtain, and from this equation Es will be Qna by putting E subscript s will be Qna times WD, because we need to put y equal to 0 by epsilon s. Now, using these two expressions of QES, so in a way we have obtained Es in two ways. One is from this area under the curve, and second is from this integral, and by equating these two expressions we can find out a relationship between the WD value and the epsilon s value, and that is, if we do a proper rearrangement, this is how it looks like. WD is equal to square root of 2 epsilon s psi s divided by QNA. Okay, and from WD we can also calculate the total depletion charge, which will be just an integration of this charge density, and it will be minus QNA times WD, so which will be square root. So the depletion charge will be minus square root of 2 QNA epsilon s psi s. So this is the classical electrostatics of the MOSFET if we look it from the band diagram point of view, and this is what we obtain by solving the Poisson equation in the depletion region. And in the depletion region, it is the most easiest to solve the Poisson equation. In other regions it becomes difficult, but one of the main highlights of this discussion is that in the depletion region the charge is related to the surface potential. This psi s is also known as the surface potential. In this way, QD is directly proportional to square root of psi s. However, in accumulation, when we apply a negative voltage, Q in accumulation region will be exponentially related to the surface potential, and also in the inversion region, because in inversion also it is the electrons, it is related to the amount of bend bending, and psi s is directly related to the bend bending, and the accumulation and inversion charge is the charge because of the mobile carriers. So that is why they are exponentially related, but the depletion charge is related in this way. So yeah, just take a note here about the accumulation and the inversion charges. The depletion charge we have calculated precisely, and I would like to think more about, I would like you to think more about how we are saying that the accumulation charge and the inversion charge are exponentially correlated to the surface potential. Please go back to the basics of the carrier statistics in semiconductors and see it there. You would find it will be pretty much straightforward relationship. So we will stop here, and in the coming class we will deal with the various capacitances in the MOSFET and the mobile charges. Okay, I thank you for your attention. See you in the next class.